Good evening. When I was young, the biggest telescope in the world was the Mount Wilson 100-inch reflector in a class of its own, and the second largest was the 72-inch metal mirrored Rosse telescope. Well, things have moved on since then. We have the 200-inch, other large telescopes, and now the largest and most powerful telescope in the world is the VLT, or Very Large Telescope, made up really of 4 telescopes, each with an 8-meter mirror working together, in the best possible site in the Atacama Desert of northern Chile. Well, some years ago, I went there, we did a sky at night from there, and the telescope was being built. Now it's complete, and Chris Lintott has just been there.
I'm standing on the summit of Paranal, and behind me are the 4 domes which house the telescopes that make up the VLT. Each one of them would be a world-class observatory in its own right, but the plan here is to get them to work together, and when that's achieved, we'll have an instrument theoretically capable of seeing a man on the surface of the moon. The site at Paranal in Chile is ideal for astronomy. Rain is extremely rare, and the whole atmosphere is almost completely dry. Not the ideal climate for wildlife, but as we're in the middle of the Atacama Desert, the driest anywhere in the world, literally nothing lives here except the astronomers. Difficult though it is to believe, this is an ancient seabed which has been pushed upwards by the process of continental drift. It bears a striking resemblance to the surface of Mars, as seen in pictures sent back from spacecraft like Mars Express. Red sandy soil, boulders, even the occasional dust devil. I half expect to see the rovers Spirit and Opportunity come rolling over the nearest hill. The unique climate of this place is easily seen in satellite images. Air, cooled by the Pacific currents, forms an almost permanent cloud cover at sea level, whereas further inland, over the Chilean Andes, the air is cooled enough to form cloud. In the middle, we have perfectly clear nights, 350 days a year.
We astronomers always want to do things better, to go deeper, to look for fainter objects. So when we were satisfied that we had a very good observatory on La Silla, we decided what's the next step, and the next step was to go bigger, and going bigger was the VLT. And the VLT was a major investment for ESO, and in order to maximize the return, we wanted to put it in the best site, and we finally determined that this place was the best for our needs.
So what have been the scientific highlights for you?
Well, there have been a lot of scientific highlights. This wonderful facility has provided us with a lot of new results and very exciting ones. One of those results is definitely, which is very spectacular, is the black hole at the center of the galaxy. We have observed the motions of the stars around this black hole. Stars are moving from day to day, really, and we could determine accurately the mass of the black hole, this distance. And on top of this, we have observed infrared flares from the black hole, which is something that had never been observed before, and which gives us access to a whole new physics. We've also possibly detected a new exoplanet around another star. And so far we have an image and a spectrum which apparently are consistent with the presence of a planet around the other star. We've been observing with incredible details the surface of satellites in the solar system, Titan for instance. And this is also very useful for the people who prepare space missions to those objects.
As you might expect from an area with skies as clear and as dark as those we have here, there's a strong tradition of astronomy among the indigenous people of Chile. In order to recognise these traditions, the 4 telescopes that make up the VLT take their names from those of astronomical objects in the Mapudungun language. And so behind me is Antu, which means the sun, Koyan, which means the moon, Melapal, which means the Southern Cross, the most famous of all the southern constellations, and then Yepan, which translates as the brightest star in the sky. What we don't know is whether they've noticed Venus moving against the background stars, and so we don't know whether they counted Venus or Sirius as the brightest in the sky. Yepan was the last of the 4 telescopes to be brought into full service, and once the enormous dome doors are open, light passes in, reflects off the 8.2 meter diameter primary mirror, goes upwards before hitting the secondary, and then coming back down either to an instrument underneath the main focus or into the giant cameras on either side of the main telescope. Now, although the VLT mirrors are the largest ever built for astronomy, they're very thin, only 18 centimeters. So as the telescope looks down towards the horizon, the perfect shape of the mirror will deform under the effects of gravity. However, because the mirror is thin, Actuators and computers underneath the telescope are able to adjust that shape, and so the mirror retains its perfect form wherever the telescope is looking. Even on a site as good as Paranal, and with all this technology, we still have the fundamental problem that the telescope must look through the Earth's atmosphere, and it's the shimmering of that atmosphere that causes stars to twinkle, and which affects the precise measurements scientists use the VLT for. Now, using what's called an adaptive optics system, a moving mirror is able to compensate for this atmospheric movement. If you like, the telescope's been fitted with glasses, and the VLT is one of the first telescopes in the world to regularly employ this new technology.
This is a quite new system which was installed in 2001, which is able to correct the atmospheric turbulences. The light first goes on a so-called wavefront sensor, which is also a camera which analyzes the images for distortions. And from this information, a very fast computer is calculating the correction for a deformable mirror,
Right.
which is a soft mirror with 162 actuators, which is able to correct the image to get a straight one.
I mean, looking through a small telescope, you see the atmosphere moving very quickly. So how fast does your mirror have to move to compensate?
Well, the system is able to correct up to 500 times per second.
Well, it's impressive. Up in the control room, we have a recent example of Yeppen's adaptive optics systems in action. The original image shows stars, but they're blurred by the atmosphere's movement. Apply the adaptive optics, and not only do the images become sharper, but you see all the faint objects in the background of the field of view.
Well, as you can see from that, adaptive optics is all important now. Sarah Kendu from University College London is working on that kind of problem. Welcome to the Sky at Night, Sarah.
Thank you.
Can you say a bit more about it?
Well, adaptive optics has become a very, very important technology. It was realised as early as the days of Isaac Newton that the atmosphere poses a very important problem when we're looking at the sky. You can see this, for example, when you look at stars, that you can see them twinkle, and that's effectively the atmosphere that does that.
Go up high in the atmosphere, and they twinkle less. On the moon, they won't twinkle at all.
No, that's right, and that's why there are also now space telescopes that try to go around the atmosphere via that method, but of course that's very expensive and has its own problems as well.
Well, down here we're at the bottom of a layer of atmosphere. We can't control the atmosphere, therefore we've got to compensate for it.
That's right, but we have to rely on models and measurements of the atmosphere because it's effectively a random process and it's very difficult to predict.
Modern computer is essential there.
Absolutely. These computations need to be made up to sort of hundreds and hundreds of times every second, and the whole loop of measurements, computations and then control signals sent to the deformable mirror have to be carried out that frequently, and of course that places very high demands on the computing power. And it's really been in the last 20 years or so, since the early 80s, that very big advances have been made in astronomy and that the technology is now becoming more mainstream.
What's your own particular research here?
My research is actually looking at technologies for these deformable mirrors. As telescopes are becoming bigger and bigger, the next generation of telescopes will measure much more than 10 metres in diameter. These deformable mirrors will also become bigger and bigger, and the technology needs to have the capacity to scale up to these bigger sizes, and at the moment that's a problem. And so I'm in particular looking at different types of materials that could be used to make them.
Well, it shows how far we've come even in the last few years. Sarah, thank you very much.
It's my pleasure, thank you.
Now, the other great advance is the use of interferometers. That means combining of the light from various telescopes so the telescopes work together. That was pioneered by radio astronomers and worked very well, but it's much more difficult with light. Back to Chris in Chile.
Each of the 4 telescopes is already in great demand from astronomers, but the VLT was the first major optical observatory to be built with interferometry in mind from the beginning. And progress is already being made towards combining the light from the 4 giant telescopes. Light from each and every telescope involved must have travelled exactly the same distance by the time it arrives to be combined. That means diverting light into loops in order to delay it, and the length of those loops must be controlled with incredible accuracy, which is what makes optical interferometry quite so difficult. I know the 4 telescopes are working individually and working very well, but you have begun to combine their light.
Yes, well, actually a lot. So already 2 years ago we started with 2 telescopes, combining them. We have currently something like 3-4 nights a month when we use at least 2 telescopes together. We have had, as always, a lot of things to learn. It gets very complicated because these big telescopes needs adaptive optics. Also, adaptive optics is a new technology.
Right.
This is working well now. Actually, when we operate with 2 UTs, unit telescopes together, it's something like 40-50 computers involved.
Wow.
It's a lot of things which has to work at the same time, and if one single piece breaks down, the whole system breaks down.
Within a year, the 4 main telescopes will be joined by 4 auxiliary telescopes, like the one in the small dome behind me. They're smaller, but they're able to move across the entire platform to any of the observing locations marked by these white covers. Here, the light will pass down into an optical laboratory where it will be combined with light from the main telescopes.
The auxiliary telescope gives us more baseline because they can move around here on this platform. You see all the observing stations, so there are 30 observing stations, allowing a maximum baseline on 220 meters. So this gives much more data points.
Right.
But the heart of the whole of VLTI is really the delay line. So the delay lines are here below. They have a stroke of 60 meters. There are 6 delay lines.
Right.
And they have to be positioned to accuracy of nanometers.
Which is why optical interferometry is so much more difficult.
Yes, exactly, because in radio you have much longer wavelength.
Eventually, let's assume you've got all of this working. What's the one scientific highlight you're expecting?
Well, now it's very fashionable for searching for planets, and with this high resolution, in principle, we will be able to see a planet beside a star.
Wow, that would be an amazing image.
Yeah, the first direct detection of a planet and not indirect.
Due to this complexity and the sheer scale of the project, it could be up to 5 years until all 8 telescopes are able to work together. But the scientific gains from the ability to see the universe's finest details make it worth the wait. Of course, even with the best telescope in the world, you need good instruments to get results. Spectrographs, like Symphony here, split the light into its constituent wavelengths, enabling astronomers to calculate the chemical composition of the objects we're looking at, and via the redshift, their distance. We use cameras as well, based on the same technology as that in your digital camera.
The red one is the infrared camera Konica, which, because it's working in the infrared, needs a very cold detector temperature, which is reached by a helium compressor to 22 Kelvin.
That's cold. And of course, on this telescope, Jeppen, we've got one of the newest instruments up on the mountain, which is Symphony.
Yeah. Symphony you can find down there in the Cassegrain focus, which is also an adaptive optic system, which is more standardized, like also the interferometry.
And the exciting thing about Symphony is that it can take spectra across a whole field of view.
Yes, correct. It is only a spectrometer. You can do a like 3-dimensional image in one shot, because it analyzes every object with respect to a spectrum.
You pick up a redshift, so you have a distance. So
Yes.
I guess it's the first 3-dimensional astronomical camera.
Yeah, you can say this.
It's sunset, but before the observations can begin, the engineers must get the telescope ready. The light fades very quickly when you're as close to the equator as we are here, but the half an hour or so of twilight we do get is a very busy time up on the mountain. First, the telescope tilts over onto its side, simply to avoid anything falling on it when the doors are opened. It weighs over 400 tons, and it's an incredible sight to be inside the dome watching it move around. Next, the doors themselves open, opening the telescope up to the sky, and then the shutters along the front, which provide shelter from the wind during the night, open one by one. Around the rest of the dome, holes open which allow air to flow freely through the dome and across the telescope. When the night's calm, like tonight, the telescope's surprisingly open to the air, and it's the wind blowing through that not only cleans the mirror, but keeps the seeing absolutely steady. The observers that are involved in tonight's programmes will have applied months ago for their time on the telescopes. The VLT is hugely oversubscribed, so it's important to make the most of every second of darkness. The technology and engineering may be impressive, but it's the science that's the really exciting part. Overnight, each telescope is operated by a team of 2 from the control room just below the summit. There's no one at all up in the domes, but a microphone picks up the noise of the telescopes, and the emergency stop button is always close to hand in case anything untoward happens. The ultimate control of the telescope lies with the telescope and instrument operator, who also monitors the conditions and the performance of the systems. Tonight, Norma Eduardo is in charge of Melipal.
We have all the information of the telescope here. We have the position of the telescope. We also have the drawing of the moon, the direction of the wind, and the information on how high is the wind.
Sure, which could cause problems.
Yeah.
Because one of the things that surprised me was how open the enclosures are. You have all these vents, these holes around the side.
It's to make the wind go through, but without disturbing too much. But the idea is that the wind cleans the surface of the mirror to get a good scene, but not to disturb too much. So when the wind starts to get high, all these things automatically start to close.
But you still need to find the object.
Yes, well, the telescope presets to the position that is given by the astronomer, and this blue square shows what the instrument is seeing. So we have to find a guide star around that doesn't vignette the field.
Right.
And this is the guide star we have here, but this guide star we use for two reasons, for two purposes. One is to guide, that is to really follow the target.
Make sure it stays in the center of the image.
And also for the image analysis.
Right, okay. In order to determine what to do
the
to
image
the mirror.
analysis is what we call the active optics.
Right.
And all the changes in the actuators are defined.
Okay. How quickly does that happen?
Well, right now it's doing it every 14 seconds.
Although many observers do travel out to carry out their own observations, much of the research is done by locally based staff astronomers who also get to follow through their own projects. Kieran O'Brien's speciality is X-ray binaries.
An X-ray binary is a binary that contains a star, much like the Sun, which is losing material onto the surface of a neutron star or around a black hole via an accretion disk. They're very active objects. They emit most wavelengths from X-rays, gamma rays, through optical and down to the radio.
And of course the VLT can be used to look at a huge range of objects and uses different instruments to do so, like VMOS.
Yeah, that's right. VMOS, as we're using here at the moment, is a multi-object spectrograph capable of taking several hundred spectra in a given shot and over a large field of view. At the moment we're observing some active galactic nuclei, which will be compared to observations at other wavelengths.
And each one of the strips on the image is a spectrum of a single object.
That's right. At the moment we're doing quite low resolution spectroscopy over a number of objects, and each one will tell about the redshift, for instance, of the target. So we can do the VMOS is known as a cosmology machine. It's designed to measure a large number of redshifts or take low resolution spectra over a large number of objects.
And that is the VLT. So far, in a class of its own and providing fundamental results. So time now, I think, to talk to the people who've actually been using it. So I'd say welcome Dr. Isabel Hook from Oxford, Professor Jerry Gilmore from Cambridge, and Dr. Alan Fitzsimmons from Queen's University Belfast. And all of you have been using the telescope for your different researches. So can I come first to you, Alan, because you've been studying asteroids and you're closest to home. So what exactly is your work with the VLT?
Well, what we've been very interested in is studying precise detail the physical characteristics of asteroids in our own solar system. And in particular with the VLT, we've been interested in a theoretical experiment or a theoretical calculation, which implies that as asteroids rotate and they absorb sunlight and re-emit that sunlight as heat, that very act can actually change how fast they're rotating. And this is important for us because we see, first of all, a lot of asteroids that are rotating very slowly. We see asteroids that are rotating so fast they're on the verge of breaking up into small
But you're dealing, are you
particles.
not, with what they call the near-Earth asteroids, those that leave the main asteroid zone and swing very close to the Earth. And these are tiny things, often less than a mile across.
That's right. In fact, the specific asteroid we've been studying is one called 2000 PH5. Now, this is only about 150 metres across, so it's actually quite small, but it does approach the Earth about once a year in July. And when it does so, actually, it's about 15th or 16th magnitude and has actually been observed by amateur astronomers. but within a couple of months it sinks down to fainter than 21st or 22nd magnitude, and that's why we need the VLT to study it.
What again are you trying to find out?
Well, what we want to do is measure its rotation rate very accurately from year to year and see whether or not this theoretical effect of changing the rotation of the asteroid actually occurs. Now, to do that, we've got to measure it very precisely. In fact, we have to measure how fast the asteroid is spinning to better than a millisecond. What we see here is a movie made from the individual images obtained with the VLT of the asteroid 2000 PH5 over a period of just under 2 hours. But if you look at it more closely, one can see it getting brighter and getting dimmer on a regular basis. And this is caused by the asteroid reflecting more or less sunlight as it spins.
If we saw one coming towards us, what can we do about it? Anything?
Well, the first thing we could do is make sure we've got the calculations right, make sure we've got the orbit as accurately as possible. And that's something that's ongoing with all 3,000 near-Earth asteroids that we know of to date. But unfortunately, at the moment, if we spot one coming towards us or on a collision course, then at the moment we have no deflection mechanism in place. Saying that, we would normally have about 10 or 20 years warning, and right now the European Space Agency is looking at possible missions to try and deflect an asteroid, so we have some time yet.
Well, it's fascinating work, and of course quite near home, but there was, when they come to you, Jerry, of course you're looking much further into the universe.
I had the privilege of having the first British run on the VLT, and it's part of a project that we've been doing for a very long time now, which is weighing things. We've known now for nearly 20 years that the universe isn't made of what we see. The stuff we see is almost irrelevant. It's important to us because we're made of it, but it's pretty well uninteresting as far as the universe is concerned. Most of reality is some completely different form of matter, what we call cold dark matter.
What is it?
Well, that's what we're trying to find out. You see, that's the challenge. So we've been working for many years with the available best 4-metre telescopes, particularly the William Herschel telescope in La Palma, and we've pushed that to its limits, and then we were ready to take the next step. And so that's where the VLT comes in. What we're trying to do really is measure how cold is cold. How cold is cold dark matter? And we do this by weighing things. And weighing things is easy. You know how to weigh things. Everybody knows how to weigh things. Essentially, we just measure how fast things are moving. And we know if stars are moving very fast or anything's moving very fast, it takes a lot of weight to hold it back. Otherwise, it will fly away. If stars are moving very slowly, it doesn't take much weight to hold it back. So if I find a little galaxy or a part of a galaxy in which the stars are moving all very slowly, I know that bit doesn't weigh very much. Similarly, if I find a part of a galaxy or a whole galaxy where the stars are moving really fast, then I know that thing weighs a lot. And so by comparing how fast the stars are moving and how much weight that Newton's laws then tell me the galaxy has, with all the stuff I can see, I can work out how much real stuff is there, how much weight is there, and that's the matter.
Which galaxies are you studying particularly? Which types of galaxies?
Well, it turns out that the key to measuring how cold is to find the smallest thing that's got dark matter in it. So we know the universe is full of this stuff. Big clusters of galaxies are totally dominated by it. Even middle-sized galaxies like the Milky Way, we now know are totally dominated by it. We also know that things like globular clusters of stars don't have any dark matter in them at all. So something in between is where we first find that stuff. And we're fortunate that there are, in fact, the 7 dwarfs. Actually, that's a slight cheat because we found a new one in the course of this program, so there are now 8 dwarfs. But there are 7 and a bit dwarfs, dwarf galaxies orbiting around our own Milky Way, like moons around the Milky Way. And these things have just a small number of stars in them. They're very hard to see. In fact, they're visually under-spectacular, say the least. You can really have to struggle to find them. But it turns out that these things are almost pure pieces of dark matter. So there's these little stars are whizzing around nearly 100 times faster than they ought to be moving, and they make these little galaxies. So these galaxies are the pieces of dark matter that exist in the universe that we can find only because there are a tiny few stars in them. So what we're doing is measuring how fast these stars are moving and how they're spread out. And from that we can just weigh the stuff. And it turns out in these little galaxies that there's about 300 times as much of this exotic stuff as there is of ordinary matter, that's stuff that makes up stars. And so this is our best place for finding out the first thing we want to know about what it is, which is how cold is cold. And we think we're getting there. And
what are the conclusions you've come to so far?
Well, this is all very new, actually. It's exciting stuff. This is almost a press release here. amazing thing, we've now done 5 of the 7 of these galaxies, and fortunately for us, they're all very similar. If we got 5 different answers, that would tell us nothing. That would mean that they've all had complicated histories and we still have a real problem. But all 5 of them look the same, and we'll know about the other 2 pretty soon too, in about 2 weeks' time, I hope. And all 5 look the same. In fact, what we see is that the distribution of dark matter in the central regions is really rather smooth. Now, if the dark matter were very cold, it would all fall into the middle. And because the particles aren't moving very far, they just stay in the middle. And so cold stuff would form a real spike, a really dense little centre. Hot stuff, very hot stuff, would be very spread out, like the Earth's atmosphere, you know, spread out over kilometres. And in between would be in between. And what we see is in between. And that's really exciting. So we seem to see this stuff spread out characteristically on a scale of about 1,000 light years. Equivalently, I can say that corresponds to a density of about equivalent to 1 hydrogen atom per cubic centimetre. So it's pretty sparse, it's a pretty high vacuum, but in every centimetre in this room there'll be 1 of these particles in it. So they're there, and that means we can start to find them. And also, if I were to convert this into a temperature, the temperature is about 10,000 degrees. So it's not cold by any means, but it's tepid. So the stuff's tepid. And we are, just for the first time, beginning to find out enough to start to say what this stuff might be. And first of all, of course, what it isn't, so we can cross a whole lot of obvious targets off the list.
Well, Isabel, your research takes you even further, doesn't it?
It does. We're doing a project to study the universe itself and its expansion rate. And about 6 years ago, our team and another independent team found a very surprising result, that the universe isn't just expanding, but it's actually accelerating.
Accelerating the universe.
Yes. And because that was rather a surprise at the time, we've been now embarking on a large project to try and confirm this result and really understand it. So we're doing a project which involves studying distant supernova explosions. And in particular, we're interested in type 1a supernovae, which are so-called standard candles, which means we know their intrinsic luminosity. And that means that if we observe their brightness on the sky, that gives us a measure of their distance.
What's the cause of type 1a supernova? Collapse of a very massive star, or the destruction of a white dwarf?
We think it's destruction of a white dwarf that's reached the Chandrasekhar mass limit from accretion from another companion star, and that tips it over the edge and causes it to explode. So we believe that they always explode with roughly the same mass, and that means that they have roughly the same luminosity when they explode, and that's what makes them standard candles.
How far out can you go?
Well, at the moment we're able to observe supernovae out to, in terms of redshift, out to about a redshift of 1.5, which corresponds to about a time when the universe was about 1/3 of its current age. So we're able to look right back across the history of the universe. And what we do is we measure the brightness of the supernova, which tells us the distance, and we also measure its redshift, which tells us how much the universe has expanded since the light left the supernova. And if you combine those two things with a series of supernovae at increasing distances, you actually get a sort of map of the expansion history of the universe. And that's how we're able to trace whether the expansion is going steadily or accelerating, as we believe it is now.
When I was born, we didn't even know the universe was expanding. It was before Hubble proved it, which is a long time ago now. And we've certainly come a long way, haven't we, since then?
Well, that's right. There are so many things that the advance of telescopes has allowed us to discover about the universe over the years and over the decades. And so, for example, if we go back to asteroids, if we look at 60 or 70 years ago, most asteroids were thought of as being lying between Mars and Jupiter in the asteroid belt, and there was 1, maybe 2 objects that were known to orbit around the inner planets, and now we know of over 3,000. In fact, we regard this as a natural state of affairs, that objects are thrown out of the asteroid belt and in towards the sun.
Well, of course, I've got a little book there written by G.F. Chambers. The first one I read is asteroids were no real interest to anybody. How wrong he was.
Well, absolutely. It was certainly of interest to the dinosaurs 65 million years ago.
Well, the VLT is now up and running. What about future research with it, and where is it leading us?
Well, in the short term, of course, it's still growing. It's really just a baby. It's only 5 years old. It might be a big baby already, but it's got a long way to go. There is to be a major instrumentation program involving the United Kingdom. So again, building on the expertise that the UK has, we will be providing the next generation, or part of the next generation, of new capabilities for the VLT telescopes, so that they will always be the best in the world.
Well, going along with that too, I'm sure.
Yes, I think one of the big advances that will come along is the development of adaptive optics on these telescopes, both so-called extreme adaptive optics for looking for planets around other stars, and also wider field adaptive optics where you can correct the atmospheric seeing over a larger field. And that sort of thing could be extremely useful for example, our supernova program, where we're looking for point sources on the background of a faint galaxy. And the better you can sharpen the image, the better you can separate the supernova from its host galaxy. So if we can do this over a wide field, we should be able to find large numbers of supernovae out to even larger distances.
I wonder what we're going to find. One point about the VLT is that from its site in Chile, you have access to the southern sky. And some of the most interesting objects are in the far south, so from England they are inaccessible. Well, Chris has been there, and he's had time to look round the wonders of the far southern sky.
It's nearly nightfall and the sun's setting over the desert behind me as the professional astronomers up at the VLT are settling down in front of their computers for a night's observing. But what really excites me on this trip is the chance to see the sky for the first time from south of the equator at this superb site. We're looking forward to sights such as Orion seen overhead, beautiful views of Saturn and deep sky objects like Omega Centauri and the Large Magellanic Cloud that we never get to see from the UK. It's going to be a stunning night. And with me are some of the world's leading astrophotographers. Damien Peach from the UK is responsible for some of the most stunning images of the planets I've ever seen. And for local knowledge, with me is Belgian astronomer Daniel Versace, who's lived in Chile for more than 5 years. We've chosen a site just 100 metres below the VLT, and coincidentally, it's the site for ESO's newest telescope, VISTA. When completed, it will be the largest telescope anywhere in the world dedicated to large-scale surveys of the night sky, in this case, both in the optical and the near-infrared regions of the spectrum. We're trying to do as much of the setting up as possible during daylight hours, because here, literally within sight of the VLT, restrictions on light are incredibly tight. In fact, it's rare for anyone to be allowed to bring telescopes up here, so it's a real privilege for us this evening. Daniel, of course, has driven up from the south of the country, but Damien's managed to pack a surprising amount of kit into his airline luggage. So Damien, you brought your telescope out from England despite the excess baggage, but you've had to make some adjustments to it.
That's right, Chris. The polar axis actually needs adjusting because we're much closer to the equator here at Paranal. Where at the poles of the Earth, the polar axis of the telescope would be pointing directly at the zenith, and it will actually track the sky around in a circle. As you move further towards the equator, the lower the axis points, until eventually when you reach the equator, the axis would actually be horizontal. And here at Paranal, the latitude is about 24 degrees, which is about 25 degrees different from back in England.
And I know you're planning to look through it, but you're also planning to do some imaging today. So tell us about the camera you've got to do that.
I've actually brought along 2 webcams for imaging of the planets, a black and white webcam and a colour webcam. Of course, the webcams remain the most powerful tools for high-resolution imaging of the planets, and what better place to exploit it?
So I know you're looking forward, as I am, to the southern sky, but what are you going to look at first?
Well, of course, I'm completely spoilt for choice here in the Southern Hemisphere. I think my first object will probably be the Magellanic Clouds, as I've never seen them before.
Well, you'll have to fight me for the eyepiece, but thanks for bringing it all out.
Of course.
While Damien's imaging will focus on the planets, Daniel has other targets in mind.
We're looking at an object in Orion. It's commonly called the Waterfall. It's a very small, dim star-forming region, and it's close to a nebula that's better known, which is called NGC 1999. It's just south of the Orion Nebula, which means up here. It's above the Orion Nebula.
So these are all part of the same star-forming complex in reality?
Yes, exactly.
So how did you come to pick that one object?
Well, I figured having traveled a long way and not being able to take a very large or long focus telescope, we're talking here 1100 millimeters, and still trying to do something in high resolution. This is like an object that matches both things. You need a reasonable focal length, and hopefully with the seeing we're going to get tonight, we will still get a good resolution on that one.
And as well as the telescope, you obviously need a great camera. So tell us about what you're holding in your hands.
We're going to be using a 6-inch telescope by Astrophysics. It's a refractor. And an ST10 digital camera. It's a CCD camera with very small pixels. Again, for the resolution.
Okay, and you create colour pictures in an interesting way.
Correct. We will take a sequence of probably 5 to 6 pictures in each color. That's red, green and blue. And then probably 8 to 10 pictures in luminance. That's the white light.
And then add them together in the computer.
And then in the computer, everything gets mixed up together with a little bit salt and pepper, and we get a nice picture. Yeah.
Fabulous. Now, you've travelled all over Chile. You've lived here. And how does this observing site compare?
We'll be able to tell tomorrow, but from the looks of it, it looks fantastic. Yeah, we are very close to the ocean. It looks like the seeing is going to be marvelous. The wind is dying down. So everything looks like it's going to be real fun tonight.
And of course, the other advantage for us of having you here is we need a local guide to the sky. I've never seen the Southern Cross, let alone the faint fuzzies, as of now. So maybe you should tell us about a few of the objects in the southern sky that we won't know about.
Sure. I mean, well, I'm Belgian myself, so I needed some time to find my way around the skies, and sometimes I'm still looking a little bit upside down to find my way. But yes, the main highlights, of course, are the Magellanic Clouds. They are deep in the south. Then we will have some other nice goodies like the 47 Tuk, which is a very nice globular cluster. We will see Omega Centauri, although it's a little bit low in the sky at this time of the year. And if we start early, we will have still a nice view of the Milky Way heading towards the west.
The Magellanic Clouds are our galaxy's most obvious neighbours. Two small dwarf galaxies, they orbit the centre of our own Milky Way, and each time they pass through, gas and dust is being stripped from them. In fact, our galaxy is actually cannibalising them. It's 3 hours after sunset, and with the moon above the horizon, it's still one of the clearest and darkest views of the sky I've ever had. And we're using a night vision lens to try and give you a flavour of what we can see from this remarkable sight. Daniel and Damien are still hard at work setting up their telescopes and cameras, but let's interrupt to get a tour of the southern sky. So let's start with the familiar parts of the sky, but there's something very odd about Taurus.
Yes, absolutely. We're seeing it completely upside down from how we usually see it in England, and the whole perspective of the sky is completely changed and very difficult to get used to. Yeah. The very distinct Pleiades cluster is really quite stunning to see.
And there's at least 12, 13 stars visible with the naked eye in the cluster. So again, it's a really good indication of quite how good a sight this is.
Absolutely. And of course we have Orion pointing at a very odd angle toward the horizon.
Yeah, the sword's hanging upwards from the belt, with the nebula, which you can see as the second star, is obvious with the naked eye. It's obvious there's something going on. Yeah. You can see the nebula.
And Sirius is also in the Canis Major there, is upside down.
Yeah, it's interesting. Sirius, the brightest star in the sky, always seems to really stand out at home through the murk and the fog. But here it's bright, but it's not noticeably bright in some of the other.
Then if we go more south, we go in the direction of the Magellanic Clouds, which of course are not visible from Europe.
I can't believe how large on the sky they are.
Yeah, they are absolutely remarkable to see for the first time.
But they're obvious with the naked eye. How do they look in binoculars and in a telescope?
Well, binoculars are fantastic for looking at these objects, and of course one object that I can't help but mention is the spectacular globular cluster 47 Tucanae, which we've enjoyed absolutely stunning views of this evening.
It's also my favourite one. The interesting thing about the Magellanic Clouds is that each one has a highlight. Close to the smaller one is 47 Tucana, just mentioned. And on the edge of the other one, of the large Magellanic Cloud, is the Tarantula Nebula, which also is also a highlight in a Dobsonian or plain binoculars.
It's also where the nearest supernova to be detected in recent times went off in 1987.
Right.
Was in that region.
Further down to the South Pole over there, Octans.
It's remarkable with the pole quite how empty a region of sky that is. There's no bright stars there at all.
That's correct.
Yes, polar aligning is. We are so lucky to have Polaris in the UK. We really are.
We've also got the nearest large galaxy in the sky. On the other side, moving back round towards the north, there's Andromeda.
Yes.
It's completely, again, a different perspective than we see it from in England. But the incredible dark skies here at Paranal make it such an easy object to see, even with the naked eye.
I've always said that you can tell how good a sight is by counting the number of stars you can see inside the square of Pegasus, and I lost count at around 30, which I suppose answers the question. So although we've bought all the equipment up here to get the best possible view, you can do a lot of decent astrophotography with some very simple equipment, like this camera here.
Absolutely, Chris. You don't need expensive equipment to photograph the night sky like we have here.
Especially when conditions are this good.
Absolutely, it's an ideal tool.
So, what sort of thing are you using this camera for?
I'm using this SLR camera to take long exposures of the constellations to capture them in detail.
Right, there's no motor or anything?
No, it's basically a stationary tripod with the camera and simply a cable release and shooting 1 or 2 minute exposures.
So what have you been pointing it at so far this evening?
Well, of course I've been pointing it primarily at the objects that I've never seen before, such as the Magellanic Cloud.
And they're so large that actually this sort of system has a huge advantage over a telescope.
Absolutely. One of the great advantages with this system is you have a large field of view, which means you can capture such objects as the Magellanic Clouds perfectly.
And so what sort of exposures are you using?
With this camera, typically around 5 minute exposures will give a very nice image.
Right, but if you leave it open for longer, you get an interesting effect.
Of course, you get a very interesting effect in that if you leave it open for long enough, you will get star trails.
Yeah, as the Earth rotates, we see the stars move, and on the camera, that appears as a trail across the film.
Of course, yes, and of course the ultimate place to point it at for this effect is the polar regions of the sky, where you can get a very nice trailing effect.
How are things going?
Fine, actually. The wind is bothering a little bit, but the seeing is good and the transparency is good.
And we just got the first image of the field.
We just got the first image of the field. I'm brightening it right here now, so we see the nebula coming through.
You can see the waterfall quite clearly.
The waterfall is coming out. We can do a quick first calibration on it.
Right.
Just... Yeah.
Oh, and you've lost all the wow, that's an amazing image already.
Yes, but it's only one single frame and it's still very noisy.
Of course.
What we have to do now is collect more frames.
In different filters.
In different filters and of the same filter as well. And then we will stack those different frames and get rid of the noise.
And end up with our full colour image.
Exactly.
I have to say, I can't believe the detail on that. There's so much nebulosity
going on, right?
Absolutely.
This area here is NGC 1999. The waterfall, and this one is a nice Herbig Haro object in red. Yeah,
that's amazing. How long was this exposure?
This was 15 minutes, and so we're going to use about 20 shots.
Okay, well we should let you get on with it. Okay. Good. If I look at the small Magellanic Cloud through binoculars, it's an amazing sight, but there's a smaller patch of nebulosity just next to it. It seems very concentrated. Can't quite make out any structure in it. You got it in the telescope?
I certainly have, Chris. And this object is the globular star cluster 47 Tucanae, and the view is absolutely magnificent.
Yes, of course, the binoculars show it, but they don't show any of the individual stars. What about the telescope?
Here in the telescope, you can actually
Let's have a look.
You can actually see the cluster resolved into many thousands of individual stars.
That looks almost as if you put a photo of it on the end of the telescope. That's absolutely incredible. You could still see the very strong central cluster.
Yes, it's very concentrated towards the core.
I mean, tens of thousands of stars in this object. It's almost a mini galaxy, but because it's close enough, you can actually see the stars. And then there seem to be some lanes. If you have a look in the outer regions, where you can resolve the stars, they seem to be almost concentrated into lanes.
Absolutely, Chris. I can also see these, and they radiate out from the core of the cluster.
Yeah, it's not something I'd seen. We have a couple of bright globulars in the northern hemisphere that we can see from the UK, but nothing like the resolution of this, nothing like the size of this one. It's incredible. It's
an absolutely amazing object compared to the M13, the best globular cluster we can see from England. It really, 47 Tucanae, shines above it.
Yeah, and of course it's ideal for small telescopes because you need the field of view. A bigger telescope would magnify in and you'd miss the splendour of the whole thing. It's just incredible.
Absolutely amazing.
It's 2 a.m. and with the Southern Cross and Eta Carina rising behind me, I'm going to call it the end of a fabulous night's observing up here on the mountain and leave Daniel and Damien to get on with their hard work. I can't wait to see the results in the morning. We should have some truly stunning photographs of this beautiful sky.
Certainly, Chris was enjoying the southern sky, and most sure that I wasn't there too. So now, on to the great new telescopes. Welcome back to Isabel. I'm delighted now to welcome also Dr. John Richer, the radio astronomer. We know about large telescopes, and one and more are being planned. And one of these is the OWL, overwhelmingly large telescope. And that really is going to be large, Isabel, isn't it?
It is. It's going to be very large. The proposal from the European Southern Observatory, ESO, is to build a telescope 100 metres in diameter, which is over 10 times the size of the current telescopes we have when measured in the diameter of the telescope.
It's in the planning stage now?
It is in the planning stage, and it's one of many that are being considered for future telescopes.
I remember a conversation I had many years ago with, of all people, Edwin Hubble, talking about the building of the 100-inch reflector on Mount Wilson in 1917. And Hubble said to me then that purely engineering problems were just as great as the optical problems. And with OWL, the purely engineering problems must be horrendous.
It will be a challenge, definitely. This structure will be similar in size to for example, the Jodrell Bank radio telescope, but made of glass and steel, and the whole structure, which could weigh up to 14,000 tonnes, has to be tipped around the sky in the same way we do with current telescopes. So it's certainly a challenge.
What about the site?
The site is very important, and there's a lot of testing going on at the moment to try and choose a site that will be just optimal for this sort of telescope. And one of the factors that we have to consider is wind, for example, which will be a possible problem because it may affect the shape of the mirror when it's in operation.
Of course, it's not a single mirror, is it?
No, it's not. The largest single mirrors that we can build at the moment are about 8 metres in diameter. So obviously to build a telescope up to 100 metres in size, we have to build it up from many smaller segments.
How many?
Well, there'll be over 3,000 in OWL for a 100-metre telescope.
Can you tell us a bit about the immediate research when it's ready?
Yes, well, it'll open up an enormous range of science. Partly just the sheer collecting area will allow us to observe much more distant objects than we can at the moment. That's the furthest galaxies that we can possibly see, possibly even the very first objects that became luminous in the universe. But also very much closer to us, we should be able to see planets orbiting around other stars, take a direct image of those planets, which has never been done before. And with a large enough telescope such as OWL, we may even be able to detect Earth-like planets around other stars, which is one of the holy grails of astronomy, to try and observe an Earth-like planet and possibly even get a spectrum and look for signs of life.
One thing we've got to remember, I think, is that all branches of astronomy now work together. Optical astronomy and, of course, radio astronomy. And John, great developments here. What about ALMA?
Well, indeed, Patrick, ALMA is a radio telescope which we're currently started constructing in Chile. And this telescope is being designed to answer some of the fundamental questions about origins of planets, of stars and of galaxies in the universe. This is currently one of the very exciting topics in astrophysics. Now, the problem is that these objects all form in very cold gas clouds. And if we want to look at these gas clouds, then we have to work at wavelengths which are 1,000 times longer than optical light. In other words, a wavelength of about 1 millimetre. So the Atacama Large Millimetre Array, ALMA, is a radio telescope which is designed to detect radiation with a wavelength of about 1 millimetre and make very detailed images of these gas clouds where stars, planets and galaxies form.
How many dishes involved?
Well, we are building 64 separate dishes. Each of those is a 12-metre parabolic reflector. And in total, that makes a collecting area very similar to a 100-metre single telescope. But we move the telescopes around this very high plain in northern Chile, and by spreading them out over a very large plain, we can synthesise the effect of a single dish up to 15 kilometres in diameter.
Of course, sub-millimetre wavelengths are of vital importance in modern astronomy.
Absolutely, and the reason is because the gas clouds out of which galaxies and stars form are very cold. We know space is a cold place, and typically in these clouds the temperature is only 10 degrees or so above absolute zero. That means they're 1,000 times colder than the sun, and therefore the radiation they emit is at 1,000 times longer wavelengths, which is about 1 millimetre wavelength.
Well, you've chosen the site in Chile very carefully. It's high and it's flat. You have to move the dishes around. Why exactly is that?
Yes, the site in Chile is a spectacular site for submillimetre astronomy. We've been monitoring the conditions there now for 8 years, and it's the driest site on Earth there we found, except at the South Pole. And the reason we need to be dry is because the water vapour very strongly absorbs wavelengths of around 1 millimetre, as people know maybe from their microwave ovens. And so by going very high, you get above the water vapour, and that allows most of the radiation from the distant universe to reach our telescope.
Could you say a bit more about why you have to move the dishes around?
Yes, absolutely. One of the great benefits of building an interferometric telescope, that is a telescope made of lots of separate collectors, is that we can put the antennas into different configurations, as we call them. Sometimes we push the antennas as close together as we can, so that in fact they're almost touching, and that gives us the very not very good angular resolution, but very, very high sensitivity. For other experiments, what we're interested in is making the very highest possible angular resolution with the sacrifice of some sensitivity. And for those observations, we have to move the antennas far apart as we can within reason.
Well, a start had been made on ALMA. There's some equipment is up there now, and when Chris was in Chile, he went there to find out just how far it's got.
This amazing site at the plateau of Chajnantor is the home of ALMA, the Atacama Large Millimetre Array. At over 15,000 feet, it's the world's highest major observing site and also one of the most spectacular. In just a few years' time, the entire plateau behind me will be covered in 64 telescopes. Astronomers are used to looking at bright objects. Optical telescopes like the VLT rely on light from stars or galaxies, whereas gamma-ray observatories study the biggest explosions in the universe. ALMA, however, will use the sub-millimetre region of the spectrum to study the secret universe of cold, dark, dusty regions. The early stages of star formation are incredibly cold, and so gas freezes onto the surface of dust grains, coating them in ice. Within that ice, complicated chemistry occurs, building up larger and larger molecules until the star ignites, heats the dust, melts the ice, returning everything to the gas, and so we see a complicated soup of chemicals, which ALMA will be able to detect. This is APEX, the first telescope to do science on the site, and like all the ALMA telescopes, it's 12 metres across. Although we don't have a carefully polished mirror, as in optical telescopes, the shape of the surface is still very precise, and that's to bring all the radio waves to a focus at the receiver above the dish. Professor Massimo Torenghi is the project director.
Astronomers are curious, and they like to explore the universe at different wavelengths. And we have done an incredible machine for X-ray, for optical, for infrared. And now it's time for the sub-millimeter, where the universe is extremely interesting.
What sort of objects do you expect to see with ALMA?
Well, we're going to see and study objects nearby, like a disk around star, formation of star. As well, we'll be able, with this machine, to probe the limit universe. We're going to redshift 20 or even 30, and we will see probably the formation of first galaxies. I think that we will discover things that were not thought, and not only star formation, but formation of what is going around the star. I think we are living in a beautiful planetary system of the sun, but we don't know how it's been formed, and we need to study other systems to understand better how our solar system has been formed.
Building work is just beginning, and a project in such a remote area requires the construction not just of buildings, but of infrastructure too, like the road which leads from the valley floor, a vast salt plain, up through the cacti which live in a narrow band up to the plateau far above. The site's surrounded by volcanoes, both extinct and active, and if I thought Paranal looked like the surface of Mars, the sulphur deposits on this volcano behind me remind me of Jupiter's moon Io. The height up here makes everything difficult. Even for filming, let alone for constructing or running the telescopes, we're having to use oxygen.
The eye is one big problem. As a matter of fact, this project is very challenging from logistic and from organization as well as operation, and is going to be something in between space and ground-based astronomy.
I can't wait to see the results coming from ALMA across the whole range of astronomy, but if you had one program to choose from, what would you use ALMA for?
I would really love to see the first galaxy form after the Big Bang, to see what kind of beast is this object, and then probably we'll understand more of universe with this observation.
Well, it's a spectacular site and probably the best in the world for this kind of research. And when it's all complete, it and OWL are going to be working together.
Yes, they will. OWL will be able to see the very faintest galaxies in the universe at some of the most distant objects, but only in the starlight. And we know already that there are galaxies which have a lot of dust in them, and that's where ALMA will come in.
That's exactly right. So what we know is that at least half of the forming stars in the universe are obscured by thick clouds of dust, so which makes them invisible at optical wavelengths. We believe these gas clouds are a small amount of dust mixed with a large amount of molecules. Now, most of those molecules we know are molecular hydrogen, but what's fascinating about them is that we know that there are lots of other molecules in these clouds which we can detect by their spectral signatures with the ALMA telescope. So already we've detected about 135 different molecules, things such as carbon monoxide, hydrogen cyanide, alcohol even in very large quantities. And as we work harder with these telescopes, we start to detect more and more complex molecules, some containing as many as 13 different atoms bound together. So this is a very fascinating field of study, because if in space it's possible to develop quite complex molecules, quite complex organic molecules, then it raises the question of how this chemical complexity might interact with the formation of life on other planets.
How can OWL come in this one?
Well, OWL is also an extremely powerful tool for spectroscopy because of its extremely large collecting area, and it allows you to take spectroscopy of very faint sources, for example planets orbiting around other stars, and that may allow us to look for the first signs of biospheres or atmospheres around these planets, and possibly the first signs of life.
Everything's coming together, isn't it?
Very much so, I think, yes. Increasingly, you can't use a single telescope to answer your astrophysical problem. You need to build a suite of complementary instruments and use them all to answer the scientific question you are chasing.
Isabel, John, thank you very much. So I wonder, where are we going to go? One thing I'm quite sure, there are many surprises in store, and personally, I always expect the unexpected. Meanwhile, when I come back next month, we're going to talk about the Saturn probe and the exploration of Saturn's big satellite, Titan. Until then, good night.